Hello and welcome to this talk. My name is Ferran Teneri. I am from the University of Nottingham in UK, and the title of this talk is Teaching Mathematics to Educate Future AI Researchers. And I would like to start with a very general term, and it is, or a general question better, and is, what is engineering? According to the Cambridge Dictionary, engineering is the study of using scientific principle to design and build machines, structures, and other things, including bridges, roads, vehicles, and buildings. So we can see this definition. You might find it more or less interesting or more or less obvious. So you can see it's a study of using scientific principle in order then to do something else. What is artificial intelligence then? Artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. So as you can see, here we have a slightly different definition, and but these two things somewhat interlink. So you see that there is the concept of design underneath. And let us take at the minute, so we can leave these definitions here, and we can take a step back and step back in time, and we can say, what are some old engineering or some, if you like, old AI solutions? So let's go to the 1st century AD in Egypt, in Alexandria, and there is one inventor, one engineer called Heron of Alexandria. And he designed essentially an engine. It was a steam engine for opening the doors of a temple. So it's some kind of first automatic system, or if you like, there is some sort of control system that opens automatically the doors of the temple. And if you think this, definitely it's classified as engineering, and if you like, it can be seen as artificial intelligence. Then we can look at this other very old invention, and which is called Qanat. So we look at another geographical area, which is Assyria, King Sargon II, 8th century BC. This was a system for irrigation of the field. So this is about agriculture, but it's an engineering solution, and it is about essentially bringing the water to the field without having the human having to do the job. And of course, using gravity, trying to understand the land, and so on. And now we move to another one. So now we move to China, 725 AD, Yi Xing, and this is a first mechanical clock. This was water-based. Here there is like the general scheme. So here we have, again, a machine that is measuring time and somehow is replacing the work of a human. Why am I talking about these things? Because in every single invention, you had a brilliant mind that was somewhat changing the world and was doing it by understanding the world. And to understand the world needed some certain degree of modeling and some certain degree of control theory, if you like. So in all these cases, the engineer / the inventor needed some mathematics. So, which somehow leads us to discuss the next topic, which is mathematics and AI. So let us look into this. If we look at the things in a certain way, AI could allow to address problems we are not able to model mathematically. So for example, that happens with the neural networks. So sometimes we do not know how to solve a problem, or in this case, we don't know how to model a certain problem. And then we use AI to solve it. So we don't know much maths, but somehow we rely on a machine that is doing the job. Or there is this other example, which is from my field of investigation. And it is when we do not really know how to solve an optimization problem, then what we do is to plug a genetic algorithm in, or to plug some other sort of meta-heuristic, which is somewhat part of AI, in order to solve the problem. But on the other hand, if we want to develop some AI, so the development on progress of AI is possible only by means of an appropriate mathematical knowledge. So if I want to develop a new algorithm, I need to know mathematics, and I need to understand how algorithmic works. I need to understand how the problem looks like. It depends. But in any case, I'm going to need some basics of mathematics in order to do any form of research or to do anything that is creative and is not just a brutal application of something that already exists. Also, mathematics may be needed to check and critically analyze the solutions proposed by AI. So yes, we can trust AI, but we might need to check what has been done by AI in a critical sense, not to let diverge from what the purpose is. So we might need mathematics also in that case. And now the question is, if we as lecturers, or if you think as we as students, do we need mathematics in our curricula of engineering, AI? I am also including computer science because this talk would be valid for a range of subjects. So we might think that like several courses in engineering, such as control engineering, but it would be true also for electrical engineering or even for civil engineering. And this would be true definitely for computer science or for a number of applied sciences. And the answer, at least my view in this, is yes, but I'm not reporting you here my view, but I'm reporting the view of an expert in education, which is Lincoln Sedlacek. And he advocates that it is needed for computer science, that was his study, and we might extend his reasoning to engineering and AI. So what does he say? He says, yes, we do need mathematics for the following reasons. The first one is mathematics teaches understanding and communication through an abstract language. So in a way, mathematics rewires the brain of the learner. So you might think that mathematics is needed in teaching and learning because it allows the student to think. So it improves the logical skills of the student, and then these logical skills might be transferred in their career. The second reason is that mathematics teaches how to work with algorithms, which is part of the formalization. And algorithms are a fundamental part of AI and appear everywhere, explicitly or implicitly, in most engineering tasks. So you might think that a task in engineering requires a certain procedure, and that procedure is essentially an algorithm. And in order to understand the procedure, we need to be able to abstract things. And that's where having an understanding of mathematics comes useful and even fundamental. Then we have another reason, and it is mathematics teaches engineers how to analyze their work. So this is related to what I was telling you before. So yes, we perform a certain task, but we might or we must be critical with our own work. So this means that we need to be able to say, okay, what have I done? Is it right? Is it wrong? Is this part right? Is this part wrong? And analyzing what we have done is extremely important. And mathematics is the instrument that allows us to reach the correct conclusions. For example, if you take an example for my field, Even if I am using a software package for optimization, eventually I might check if the result is sensible. So if you think about a control problem, so if you are tuning the parameters of a controller, you want to make sure that the poles of the transfer function are not excessively close to the instability region. So this would be another reason. Fourth reason, a lot of AI engineering still involves mathematics. So many engineering tasks require a knowledge and understanding of mathematics. So for example, the design of a controller or the analysis of stability, which is what I'm telling you. So if we are performing some sort of design, we might need to know some mathematics beforehand. Now, having made this premise, which is, yes, we do need mathematics, now we get to somehow to the core of this talk, and it is this research question, and it is how to successfully teach mathematics to computer science and engineering graduates. And a sub-question is, how can we teach to our students to educate future AI researchers? So we want, of course, to teach mathematics to ultimately generate new researchers. And the question is, how shall we do it? Do we teach mathematics to engineers the same way as we teach to mathematicians? Or is there something different? Now I'm going to give you my perspective as a lecturer, as an experienced lecturer of mathematics for computer science with an engineering background, and as a very as a research active member of staff. So I will tell you my view, and I will try to formalize on the basis of what I've done. So at first, what's my standpoint? Over the past decade, possibly over the past 15 years, actually, I've been teaching mathematics for computer science. And after several years, I have written a book, then came up in the second edition, which was published in 2019. And the book is called Linear Algebra for Computational Sciences and Engineering. So this is my standpoint, which comes from years of teaching mathematics to these types of cohorts, and writing a book which is out there. It has been reviewed. It is an established piece of work that is available on well, online or in the market. So well, it has a focus on algebra, but essentially it is about most of the mathematics that a computer scientist needs within their career. So now the issue is, what's special in teaching mathematics to computer science or to engineering? Or if we like, what are the specific challenges, what's specific in the students? So many universities do not have some specific mathematical prerequisites. So in general, you might find that on an engineering course, the students might have a very diverse background and preparation in terms of mathematics. So some can be very skilled because they studied that sometime at school, while some others are not so skilled because they are maybe more application orientated, or they come from a different type of, let's say, school or applied studies. So we want to make our lecture to be suitable to all the types of learners in our environment. And the second issue is that part of the cohort is likely to not fully appreciate the importance of mathematics within their curriculum, which means that some of them, during the lecture of mathematics, they might ask themselves, or they might wonder, do I really need to know this? Or this is just some kind of part of my learning, and it is just a tick boxing exercise, something that I have to do, but that I don't really need ever in my professional practice. So let's say these are the two issues that I'm going to address in this talk. And let us start from the first one. And it is, how do I handle the diversity in the classroom? Where diversity means that some students might be very skilled in mathematics because what they have studied, and some others are not. The underpinning principles are no compromises should be made on the content nor on the mathematical rigor of the lectures. Mathematics is mathematics, and we are not supposed to simplify, or if you like, we are not supposed to dumbing mathematics down for the students that might come from a weaker background. But the way mathematics is taught to students of computer science and engineering should take into great account the composition and features of audience cohort. So I should consider whom I'm teaching mathematics. So it is true that mathematics is that one, and I cannot oversimplify it, let's say, or I'm not going somehow to remove the proofs because people don't understand it. But it's also true that I have to consider who are the people I am teaching mathematics. So if the cohort is skilled, then I have to teach in a certain way. If it is less skilled, I have to teach in another way. And in this case, I have to consider what they are. It is not true, to make myself clear, that my lecture as a lecturer remains the same regardless of my audience. My lecture needs to adapt to the audience and needs to take the audience into account the same way as we take into account who is the person we are talking to if we are having a one-to-one conversation. So there is no point in overcomplicating or having a very technical conversation with a person that is not able to understand because comes from a different field. But let us get into the details. So what have I experienced and what have I formalized in my book? Every topic can be presented in different ways, or better, can be presented from different perspectives. The first way is I teach a topic by means of formal mathematics. So, and this is supposed to target the students that have strong mathematical skills, and they are already good, so they are able to follow the formal mathematics. But then I'm immediately going to re-explain the same topic in a different way, which is by abstraction of an example. So that means that I take a numerical example, and out of that, I try to derive the rule. So this is going to speak to the heart of students that might be not very strong from a logical perspective. They might not have really studied mathematics much in advance, but they might grasp a general idea at the intuitive level, and they are not discouraged then to go back and study mathematics in a formal way. And the third way, which is typical to, let's say, the AI area, so to computer science, to engineering, and so on, and it is by algorithmification. So what does that mean? It means that there is something in common in a cohort of engineering or in a cohort of computer science, and usually they are able to either to program or to look at tasks as something that can be solved by step-by-step procedure. So I call that algorithmification of formal mathematics. So I can do the same with something abstract, with something extremely theoretical, and I can explain something theoretical as a procedure so that they are going to understand it at a certain level. And so they are going to have these three different perspective of understanding. It's not really a layered system, because I cannot say that one is under another, but it's definitely a perspective system where, of course, the formal mathematics is the one that allows to look at things the most in depth rather than these other two. So let us look at the scheme, which maybe clarifies, let's say, the interaction between teacher and learners. So we have got a mathematical concept here, and here it's explained in this first way. In yellow, I'm indicating the students that have got a strong mathematical background. So at the beginning, they are able to get what I'm saying, while probably the others that do not have a strong mathematical background are just going to wait and wonder and what's happening and say to wait what I'm going to say next. And what I'm going to say next is the abstraction by example. Of course, this next is not necessarily temporary, meaning that I might start with the abstraction by example. It depends on the topic. But anyway, let's say abstraction by example. This one is going to be the preferred system by students that do not have a mathematical background, or at least a strong mathematical background. But it might happen that some that have a mathematical background are going to like this because they are going to reinforce their initial understanding of formal mathematics. And eventually, by means of algorithmification, I have a mixed cohort of students that are going to like what I'm saying because they are going to understand it. So it can be some with a mathematical background, some without. But then when it comes to revision, those students that at this level understood something, even though they did not have the basics of mathematics, now they are ready to go back to revise and to abstract the concept and understand formal maths. And while the students that at the first level had already understood the formal mathematics, they are now able to reinforce their knowledge by during the revision by making examples. And here we have, again, a mixed cohort of students that are, let's say, revisiting the concept and understanding it better. So this is somehow the theory, or the, if you like, the assumption that I made. And well, it has been made by observing for several years, let's say at least 6 years at the Montfort, the reaction of, the Montfort was my previous university, the reaction of the cohort. And then I was every time going back and rewriting another bit of the book in order to make sure that others were understanding. And that was going on for a while. So I was going back, say, okay, these are the revised lecture notes. They were coming back. And so there has been this process that built up year by year. Then when the first book, the first edition of the book was ready in 2016, then I realized that it had to be improved a lot. And so I started writing the other one. So essentially, I added material, but I rewrote everything that I have done before. And then it came up with the new one. Okay, so this is the scheme. And now I want to explain something in practice. So I am taking one topic and I'm showing you the 3 different perspectives on how I am going to teach this topic. So the topic is LU factorization. So I quickly mention what it is, but it's mostly to define the notation. I believe this is a well-known concept. So this is a system, is a method, if you like, to solve systems of linear equations, which are equations of this type. And this equation can be formulated as a matrix equation of the type AX equal B, where B is a vector here of solutions. A is a matrix A11, A12, A1n, as you can see, and X is a vectors of unknown. And LU factorization means that the matrix A gets factorized as LU. So I express A as a product of a matrix L by a matrix U, where L is a lower triangular matrix. That is a matrix that has got zeros in the upper part, 1 on the diagonal, and something else that is non-zero on the lower part. And U is an upper triangular matrix. In this case, all the upper part is non-zero, including, and I make no assumptions about the diagonal element. So what I'm saying is I have a system of linear equations that is of the type AX equal B, A get factorized as LU, then I have LUX equal B, which then allows to solve two easy system linear equations that can be easily solved by substitution, rather than solving one that is complex and that would require a great effort, especially if the matrix A is large. So that means that UX is posed equal to Y, then LY is equal to B, and then we have the other system UX equal to Y. So we have a complex problem, and then we complex in the sense of difficult, and then we can solve this problem by factorizing the matrix, and then we end up with two straightforward systems of linear equations. This is the premise. So what happens if I have to explain this by means of formal mathematics? I need to introduce this theorem, which is let A be a matrix essentially belonging to Rnn, where Rnn is the set of all square matrices of order n, and let us indicate with AK the submatrix having order k composed of the first k rows and k columns of A. If the determinant of AK is different to 0 for k equal to 1, 2, and then there exists only one lower triangular matrix L having all the diagonal elements equal to 1, and exists only one upper triangular matrix U such that A is equal to LU. So this is the theoretical foundation of the method, which tells me that, yeah, under this hypothesis, there is only one way I can factorize the matrix. So I know that there will be only one solution, only one way to solve this task. And and then knowing that I have only one way, now I have to show what the way is. So if this is the matrix, briefly, and I want to get to that matrix factorized as the product of this matrix L and this matrix U, I have to impose that A is equal to LU, which means that I have to impose a set of scalar products, which are given by this equation, which is also this equation here, and then for I and J, 1, 2, n, in the case of I less or equal than J, so which means in the case of the triangular upper part of the matrix, then we have this formula here, which then I would read. I can read it for you, but I can let you read here actually. So sum for k equal 1, lik, lik, ukj. So I would go through this, and actually I will show how this is coming from, and it's coming from a scalar product. This can be easily verified. So, but anyway, this would be the approach. And then if I move, let's say, this term on this side, or if you like, if I move this term on this side here, I obtain the equation to calculate the Uij elements of the matrix U. And as for the matrix L, I have to use this other formula, which again comes from the scalar product, and then I end up with this formula over here. In reality, even though this is not really tough mathematics, a first-year student of engineering might already feel lost if they did not study mathematics, advanced mathematics at school. And they might find this notation unfriendly. They might feel disengaged because they might feel lost because of all the symbols. However, this is how the method is. So what I would expect after having taught the topic from this perspective is that a part of the course is going somehow to understand this well enough, and another part is going to be puzzled. But that's not the end of the world, because then I would move to this other explanation of the very same topic. And I would say, look, there is this system of linear equation, which doesn't look scary at all. It's a 3x3 system of linear equation. And this corresponds to a certain matrix A, which just simply means that I take the coefficients here and I write them here in this way. And here, I want to represent this matrix A by L and U. And all I have shown you before is nothing else by performing a one by one the scalar products of row by column, or if you prefer, it's simply the product of two matrices. So of course, you students must know the product of matrices, but if you know that, you are able to understand this. So by performing the product, we end up with these equations. So just putting the numbers over here, and then we can observe that this is a system of equation, which is of course non-linear equation, but it doesn't matter. What matters is that we have got 12 variables and 9 equations, which means that they are not enough. So where are the other equations? The other equations are L11 is equal to 1, L22 is equal to 1, and L33 is equal to 1, which is why we are imposing this. And once we have imposed that, we can simply find all the parameters in one go. So this would mean, okay, you see the example, now we can abstract the rule. And now that you can abstract the rule, you can go back to what we have seen before, you substitute the numbers with the letters, and now you're able to understand the theory that is underneath. And this is a way better than giving the theory and then walking away from the classroom and let the students figure out, because they might not figure out. And then, okay, of course, we end up with this product of matrices. So at last, I want to show you the algorithmification of formal mathematics. So again, we take a step back, we say that we want to perform the LU factorization, which means this. Now we are familiar with this. And we have to find all Lij and all Uij. What do we do? At first, we perform a mapping of the matrices, which means that we are representing the matrix L as a vector of rows, row 1, row 2, row n. And the matrix U is represented as a vector of columns, U1, U2, Un. And then we do effectively the same thing, but from a slightly different perspective. We are going to perform the scalar product. We have two vectors, so we can perform the scalar product. So the general scalar product is this one, over here. And if the equations are performed in a certain order from each scalar product, an element, Lij or Uij, can be calculated. So if we perform the operations according to a certain order that we pre-establish, then we can build up, let's say, the matrix L and the matrix U, but in reality, we are building up a matrix B, which is a combination of the two. According to the positions, we are ignoring all the positions where there are zeros, so we are just merging, in a way, these two. So this is we can think about this as a data structure, and we are building up this data structure little by little. How do we do it? We do it by means of this algorithm. At first, we copy the first row, and then we check what is happening. So I would enter here in the details, but as you can see, there are several ways. This is the crude algorithm, but okay, it doesn't matter. So from this equation, we substitute the available value from B, and we calculate this. Or we move here, and here we have a procedure that can be, of course, explained step by step and in details. And the student can see, oh, okay, so if I have, in the general case, a system of linear equation, I can simply apply this procedure, and I will get to the solution. And then I can understand this procedure, or I can even implement this procedure if I want. So So there is a perspective of looking at this, of looking at LU factorization as a computer program or as an algorithm, which is something that pretty much everybody understands in a computer science cohort, and pretty much everybody understands also in an engineering cohort. And of course, at the end, you have this matrix B, that is what we have seen before. Now we move to the second issue of this talk, and it is handling reluctance to mathematics. So, have we said, some of the students might perceive mathematics as something alien to their degree, as something that they are never going to use in their professional practice. And when they think that, they are actually wrong, because they are most likely going to need it at some point, or definitely they are going to need it if they are going to make a difference in the society and if they are going to do something important in their lives. The question is how to keep the full engineering or computer science cohort engaged and interested in learning mathematics. So what do we do? Again, here, on the basis of my experience, I kind of built up this method that is, or this technique made up of two parts. One is to report the links between mathematics and engineering computer science professions. So this is what I mean, or somehow what I mean when I say that I have to consider who is in the classroom. So I have to think what they want to hear. Probably some of them are already fantasizing about the future and about their job. So it's important to look into the market, in the job market, and to tell them, okay, look, I'm teaching you this because if you are going to do this job, you are going to need this mathematical instrument to do this thing. And that is happening all the time. And it is an exercise also for us as lecturers to reflect and to say, okay, what are we doing? Why is this important? How can we improve our teaching? How can we be more clear and more professional and make a difference to our students? And there is no big deal of making an explicit reference to links between mathematical theory and professions. The second is to share personal experience of mathematics in research profession. So, which somehow means that while I am explaining something, especially when it looks hostic, abstract, and without a clear application, I share the experience on how understanding that thing helped me to do some research and to achieve some research funding that I was not able to achieve without an in-depth understanding of mathematics. This is what is called in education research-informed teaching. And there is a very nice article about this, which essentially categorizes the different types of research-informed teaching. Here I am reporting 3 types that apply to this approach. One is called research-led, which means that I illustrate the research. I give an idea of what I'm doing in my research. Then it is research-oriented, which is I explain the research methodology. So, for example, I am explaining a statistical method that is needed in order to compare algorithms. And then we have a research tutored, which is we try to have a critical discussion about research. So, well, in mathematics, since it's not really social science, you don't really allow having opening discussions because people are not really entitled to have opinions in mathematics. However, we can have an open discussion about how a certain topic can serve us in the future, and what can be done, or for example, what is open. So if you are looking into unmanned cars, or self-driven vehicles, then you might think about this is an open problem, and there is this mathematical instrument. We don't know yet where we are going. And so you are kind of simulating some sort of conversation between the students. And then there is also another aspect, and it is the one that is more psychological, and it is to share the professional experience, to be somehow inspirational and to promote reflections about their own skills, the passion for research, and somehow to their ambition. So in a way, what we hope as lecturers is that we tell things we are proud about that we have done, and then we hope that some of the students say, okay, yes, I want to be like that lecturer. I want to do the same thing, and then I'm more motivated this week to study extra hard in order to better understand this mathematical concept. Let us get into the details. The mathematical concept they've chosen here as an example is the concept of eigenvector. Eigenvector is a very interesting thing in algebra. And I must say myself, even after many years, every time I study it, I think I understand it more. So in a way, I think that I am still learning it. And it's the same as the concept of determinants, that you always find a new perspective to look into the topic and to understand it more. So to give you one easy interpretation, just if you are not very familiar with it, if we have a linear function f of x of n variables, which means that x is a vector of n elements, an eigenvector is a special vector direction such that f of x is equal to lambda x. Or in other words, we have one special vector direction that make the function behave as a multiplier. So instead of having some kind of complex linear composition, we have a simple multiplication of a scalar by a vector. Or in a graphical way in 2D, you see that normally a linear function means that you have a certain vector, x, then when you apply f of x, you have a rotation and a change in length. That's what a linear function means. And if the vector is a special one, so there are some vectors in the domain that behave differently because it makes f of x equal to lambda x, so it is on the same direction. So you see they are on the same line, and that means that this function is behaving like a multiplier in those specific cases. To find those directions is a very important thing, and it has got a number of applications in computer science, in engineering, in optimization, definitely in control theory. An important thing that is, of course, related to this is that a function of n variables has got n eigenvectors. Then they can be linearly independent or not linearly independent, but that's another story. I'm not entering into those sort of details. But if the function is of a certain type, finding these directions has got another deep meaning, and it is I can see these n directions as a new reference system, and within this new reference system, the function behaves like a multiplier along all the directions. So the variables become independent one from another. This process is called diagonalization. The reason why it is called diagonalization is that in algebra, in a multivariate linear function is identified by a matrix, so is expressed by a matrix, which here I'm indicating with the letter A. And the eigenvectors are n vectors, which are also a matrix, that are the columns of this matrix P. So what I'm saying is that it is diagonalization, because if we perform this transformation here, we obtain a diagonal matrix. Or in a more intuitive way, we might think that we have a system of reference, a reference system, that makes our linear mapping diagonal. So we have only one variable per direction. So why do we do this thing that looks so odd? For example, so this is like from one example that comes from my lecture, and it's about one AI profession, which is data scientist. Several students these days want to become data scientists because they see that the job market is there. And so they think that if they are data scientists, they are going to have good jobs, they become managers, they are going to have great salaries. But to become a data scientist, you might need to solve problems with a lot of data. And when you have a lot of data, you might need to be able to extract information or somehow to navigate the data in a certain way. And data can be viewed as multivariate distributions, which means a distribution of vectors. And they are characterized by a mean vector, just like all the distribution, and the covariance matrix. So if you're not familiar with this concept, if you have a set of numbers, a sample of numbers, you can calculate the mean value and the standard deviation. And this is true in one variable. In many variables, what is a mean value is a mean vector. And what is a standard deviation becomes a covariance matrix. Well, it's more or less like this. This is actually the equivalent of a variance, but let's say they are closely related. It's just a matter of squaring things. A covariance matrix can be interpreted as a linear mapping itself, and its diagonalization allows the detection of the directions of the best fits of the data. So, the directions that best fits the data. So this is called the principal component analysis. So what does this mean? It means that I'm going to interpret the data, and I'm going to find some directions that make the data more readable, more understandable. And I say really what it matters in order to understand a certain phenomenon that depends on a big data set. So this is a classical method called principal component analysis, which requires an in-depth understanding of algebra. And it's one of the basic things that the data scientist needs to know. Because this principal component analysis ultimately tell you which variables are those that are really important, and especially the one that is, in some cases there can be only one, that is the one that really matters in order to control a certain phenomenon. And this, of course, has plenty of applications in AI, and it's important. But without eigenvectors, this cannot be understood, because you are going to need the eigenvectors to diagonalize the covariance matrix, and then to find the principal components. And then I have my own research in AI, and then I can show you one case of eigenvectors that play an important role in optimization. In this case, I'm going actually to point out something that I'm currently working on, that it's not even published. So when the optimum of a multivariate function is searched, a set of candidate solution can be interpreted as a multivariate distribution. So if only a distribution of points whose objective function value is below a threshold in a minimization problems are saved in a data set, then distribution describes the geometry of the optimization problem. So what I'm saying is, okay, this is a well-known fact, that if I have a certain problem of minimization, of optimization, and I sample points in the domain, and I choose those that are below a certain threshold, in the sense that those whose function value is below a certain threshold, then I am ending up with a distribution of points, or with a sample of points that describes the geometry of my problem, of my basin of attraction. Okay, don't worry too much. So let's say that I can sample some points that describe the geometry of my problem. If I understand the geometry of the problem, then I'm able to solve it. the diagonalization of the associated covariance matrix, so this looks a bit like the PCA, but there are some major differences, but we'll not enter into that. That means the detection of the eigenvalues allows me to find the reference system that makes my algorithm very efficient. And so I can find, and that's really what I'm interested in, the direction with the maximum directional gradient. So I want to find those directions that along which the function is very steep. So this might not be too clear now, but it's to say there is something that is very close to my heart and that I'm currently working with, which directly depends on something that I teach in year one. And therefore, students in year one might want to know that what they are doing is not worthless, is not useless, but it is something that helps a lot of people like me to do their research work. We can see now this example. So this is an optimization algorithm. You can see it's moving horizontally and vertically, like these two lines. And these are like, they are actually also eigenvectors, but they are eigenvectors of the identity matrix. But then it sampled some points in order to understand the geometry. So you see the AI, and then it corrects direction. So it corrected the first time. Now this is like local run number 4, and it's progressively adjusting the directions. And these directions are nothing else but the direction of those eigenvectors I was talking a moment ago. And you can see how this is optimizing the function. And having an understanding of what the right direction to explore the domain are, it's really fundamental. It allows to move very quickly towards the end. So I'm going now to briefly present a case study. The case study is about what I have done between 2014 and 2019. So we have got 4 cohorts in year 1 and 4 cohorts in year 2. The cohort in year 1 started in 2014 and continued. So we have I had the year 1 in 2014, 2015, 16, and so on. Until the year 2017-18, and I had the year 2 in 2015, 16, and so on until 2019. And I observed and I experimented this system of these teaching methods, both these teaching methods on my cohort of students. So at first I have to tell you that the assessment of each module was composed of 2 classroom tests that were done during the year and 1 final exam. And each piece of assessment had the same structure. So 50% were numerical exercises and 50% were theoretical questions, which required that the students had to learn, let's say, the proper mathematical approach with formal mathematics. In order to pass in the British system, we need 40 out of 100. But what is called the first mark, which is let's say what is a good mark, is a 70 over 100. So that's like so if a student gets at least 70, then has done very well, but 40 is a pass. So what I'm saying is that I have therefore studied this teaching methods over the years, over year 1 and year 2. So bear in mind that of course, the students that were in year 1 in 2014, then they were the very same students in year 2 in 2015, and so on, because I was teaching mathematics in year 1 and in year 2. This is the trend over time of their marks, the average marks. Here we have the standard deviation bars, and you can see that the black trend is the year 1, which is somewhat easier. But still at the beginning, you can see that they were struggling. But then the more I was realizing and including elements over elements, the better their performance, the easier they were finding to study and to learn. In year 2, so I had the first cohort in 2016. So you see, so here, then apart from this fluctuation, there is also an overall increase of the marks. Still, they are slightly lower than those in year one, but as I said, possibly this can be due to the fact that the topics of year one are somewhat easier. But still, the results are pretty good. And this is another interesting graph, which is a scatter plot, and the scatter plot of the marks against the prior mathematical knowledge. So here you see the score between 0 and 100 of what they knew of mathematics, which comes from their mark from school, the type of mathematical studies they did before. So it was normalized in this way. And this one is the mark that they were getting at my exam. As you can see, there is a certain bias in the sense that those that had no mathematical knowledge, well, some of them passed, some of them failed, but none of them really got a great mark. But then you see that it is not true that those that had necessarily a lot of maths at the beginning, they performed that great. Well, depends on the individual, but still there is a certain bias. So to have, of course, to know some mathematics in advance might have helped, but it's not the only factor. I mean, the best performance was obtained by this student here, which had more or less, let's say, was in the middle, just above the average at the beginning. And here we have year two. The results of year two are very different, meaning that at this point, there is no correlation anymore between their mark at my year two exam or my year two module and their prior mathematical knowledge. Now, in year two, after that they have been through the process and they have learned the things with me in year one, in year two, it doesn't matter what their background is. If they have nearly no mathematics, they might still score 100 or so. So probably these were not, in year one, maybe we're scoring like 50 something, but then in year two, they completely caught up other students that had a lot of mathematical background. So this was definitely a pleasing result because it means that the teaching method is inclusive and rewards the hard work of people within the modules, and does not really rely on the prior work that they might have made in previously. So, in conclusion, mathematics is the backbone of AI research and must be part of engineering and computer science curricula. There is a specific way to teach mathematics to the students and to keep them engaged. The methods has been tested on year one and year two students for 5 years and displayed excellent results for students' performance. The case study indicated that the methods removes the initial bias that is at the beginning due to prior knowledge. And the main message of this talk is every student, if taught correctly, can build a strong mathematical basis to eventually become an AI researcher. And this slide concludes this talk. Thank you very much for your attention. If you are willing to contact me, please, this is my website. Have a look before sending me an email. Of course, this office number is not going to be active, at least not at the minute. And here there are my data. Drop me an email if you need it. And I can now stop sharing. And thank you very much for your attention.